Imagine a planet on which the water is so acidic that it feels like a hot spa. Heat seeps into the ocean depths, making it difficult for sea life to build their shells properly. This leads to water that is too hot for the sea to remain in and cannot contain enough oxygen for animals to breathe. Water levels are increasing as a result of ice melting, swallowing entire communities along the coasts, flooding sewage systems and dumping years' worth of stored waste into the ocean. Hazardous crimson tides of poisonous algae. And that's only the start of the horrors that people experience on land in cities. Urban heat sinks increase high-temperature days, and every new heat wave results in thousands of deaths due to electrical overload. People who use air conditioning frequently die in the summer when trying to escape the omen of our bodies, which are not designed to withstand the intense heat of the current climate, which occasionally overwhelms us. Over time, expansion joints in older bridges cause structural issues that make them unsafe to traverse. High heat in urban settings can also damage foundations and degrade underground systems, groundwater into rotting microbial breeding sites, even at higher altitudes. Even with a little drop in temperature, structures and roads are still battered by heavy rains and higher storm severity. As the terrain changes, summer fires grow more frequent and cause road washes and landslides, fall flames that rage all year long, spewing smoke into the sky, cause long-term lung harm in people in broad socio-economic strata. Even though these fires are not perpetual, they are the ultimate blow to the temperature-related biomes we currently inhabit. As precipitation changes, our forests are rapidly overtaken by more fire-resistant ones. Settings, even slight temperature variations can have significant effects, but what could those effects entail for earthly life? In the world we live in, our basic infrastructure started to collapse a while ago. Although this extreme ideal situation appears unattainable, the reality is that this type of climate already existed on our planet 56 million years ago. The world's temperatures have increased rapidly, potentially reaching an average of about 15 degrees Celsius higher than now, resulting in remarkable modifications to the ocean biomes on our globe and landscapes. The Earth's temperature has fluctuated during the past 50 million years, but in the other direction, the Earth has cooled from a hot surface to an ice sheet, once more producing a house cold unseen in over 250 million years, leading to astounding worldwide adaptations, and one of those changes may have been us. How warm was the Earth's past? January 1987. An odd ship stops drifting in the middle sea of Antarctica, is vividly white and deep blue as it sets the 62-meter-tall structure that sets the Joyeux Resolution distinct from other ships. Towering structure above it is a crane for an event rather than a sail. Larger structure below the vessel, a drill pipe that can dive more than 8,000 meters below the surface of the sea. As seen below, the Joyeux Resolution started as an oil drilling ship, but is currently on a scientific research aim. Not the surrounding water, but a team of 25 experts wait to see what's hidden deep beneath the soil, eagerly awaiting the drill's descent through about 3,000 meters of water. Over the following 27 hours, the drill will be used to bore through the seabed. Pipe retrieves 2133 m of the compressed Earth's past in a certain area, draws the scientist's attention, a strangely red coating of clay that stands out against the typical 20 centimeters of brown, gray, and green ocean debris that envelops it. This modest mud tube would soon demonstrate the existence of an amazing climate. Occurrence: 56 million years ago, the Antarctic continent had a balmy 15 degrees C at the coast, much warmer than the sub-zero temperatures the area experiences. Day fossils from locations like Seymour Island in Antarctica provide this exotic, lush planet with additional context. Conserving the coastline of Antarctica's ferns, conifers, and blooming plants for a while grew temperate rainforests. Evidence from animal fossils indicates that it was the habitat of oddly discordant forae, such as enormous penguins and tiny sloths that live in trees. But how did they determine these temperature values using a straightforward mud tube? That the climate altered in any way, particularly so profoundly in the past, provides some of the first indications of cultural comprehension of climatic change, particularly in the form of fossils. Plants from a Chinese scientist called in the year 1080, possibly the oldest. In addition to being a prolific monograph writer, Shen Kuo was an enthusiastic geologist who wrote much before the Western age of science about sedimentary rocks and changes in the landscape. Shen was examining a landslide next to a riverbank when he came to a bamboo stalk forest uncovered during the bank collapse. Everything he saw had become fossilized stone. Although China at the time knew about trees and other flora, Shen was shocked to learn that this bamboo forest was kept in a region too arid for bamboo to grow. Therefore, he hypothesized that somewhere in the distant past historically, the region must have had a quite different environment, one that was foggy and moist, comparable to those where bamboo grows. Generally speaking, when an animal or plant is found preserved in a location where it does not and cannot reasonably exist today, fossils of all types may attest to the fact that climate change is occurring, provide valuable insights on historical climate, but many go beyond merely summarizing the ecosystem as a whole. Numerous plants and animals have extremely exact needs for temperature and precipitation, which can provide things that the oil shales of Middle Germany today include a particularly well-preserved example. Grows a temperate woodland habitat with quite chilly winters and hot summers. The average annual temperature is above freezing, but the Reg area is visible through thin mud deposits from an old lake. 47 million years ago, things were very different. Primates, prehistoric horses, and turtles are only a few of the extraordinary fossils discovered here, and the deposit also retains two further accurate markers of climate today. Crocodiles and palm leaves through palm trees evoke images of idyllic tropical regions. Certain species can withstand some degree of cold, but the most tolerant palms normally inhabit regions with winter temperatures below 10 degrees C on average. Days are warm and don't freeze much, which gives Messel a lower bound. Couldn't have had a lot of frozen days during the winter. To be more precise, the crocodiles are ectothermic creatures, and the sun and other sources of heat. On chilly days, they find it difficult to move and digest their eggs. They also need heat to develop, necessitating a warm summer or springtime to hatch. Modern crocodilians can't establish a population anywhere with an average temperature below 14 degrees C, raising the heat limit above that of palms and discarding any useful old large fossils known as thermometers are also found in little items like pollen and algae. Unique growth requirements. Locating them calls for perseverance and a microscope, but knowing when they're present or absent might be helpful. Mentioning the climate, but keeping in mind that Messel has to have been higher than 14 degrees Celsius on average does not explain why that occurred or why it altered. And just as we weren't always aware that the environment would change, we weren't always aware of how or why. Either way, not until 1824 did a French mathematician by the name of Joseph propose that the atmosphere might hold on to heat, the understanding of a unique form of energy known as black heat, what we would now refer to as although our sun and any other heated object emit infrared light. Since infrared radiation is so long wavelength, we are unable to view it directly. Its light waves also travel farther. Our planet absorbs solar heat rather than releasing it back into space. The sluggish passage of solar radiation through the atmosphere implies that the dark heat was trapped by our atmosphere, which functioned like a greenhouse, maintaining the Earth's warmth. But the gases slowing down in our atmosphere were unknown to Fourier. Eunice Foote, an American scientist, would discover a few decades later, in the dark heat of an experiment, that Eunice meticulously filled glass tubes with various gases, such as carbon dioxide and water, in a straightforward but elegant manner. She inserted the tubes and sealed the thermometers inside with vapor, nitrogen, and other substances. When the light and accompanying black heat from the sun struck the glass, she noticed that the gas was starting to release. She soon saw that as everything heated up, carbon dioxide not only warmed the most but also cooled down the slowest. She was the first of many to examine how carbon dioxide affected our planetary warmth. Her findings were subsequently verified in comparable experiments by an Irish physicist, and the future, when it comes to climate science, carbon dioxide, or CO2, is a very important and significant heat-retaining gas in our atmosphere, allowing us to utilize it as a thermometer for earlier climatic conditions. CO2 indicates a warmer era, which implies scientists haven't restored historical atmospheres dating back up to 800,000 years by utilizing air bubbles that were preserved in ice cores from Antarctica and Greenland. Although there hasn't always been ice in a deeper investigation, we require a stand-in that can demonstrate CO2 amounts, even if the carbon dioxide itself is not preserved. Instead, exchange gas is used sparingly. When there is a lot of carbon dioxide in the atmosphere, plants can breathe more readily and have fewer holes on their lower surfaces. Holes when carbon dioxide levels are lower, forcing leaves to make up for it. We can learn a lot about past CO2 levels only by examining the holes in fossilized leaves, but most typically, CO2 is measured by examining the carbon itself, which can be discovered preserved within plant cells, where plants favor breathing in carbon-12. The most prevalent type of carbon in our atmosphere, yet there will be less of it when atmospheric carbon levels are low. Selective and start absorbing more carbon-13, the bulkier, more clumsy isotope, and so on. When these levels in plant fossils are taken into consideration, it is possible to reconstruct how much carbon dioxide was in the atmosphere. With the help of these and additional proxy techniques, scientists have established a respectable record of atmospheric carbon dioxide during the last 500 million years, making it a respectable image of the planet's climate, and the narrative this data tells is just one of many over time. The world has alternated between hot and cold climates, high carbon climates, and significantly lower carbon icehouse climates. The world's waters were warm and balmy 500 million years ago, offering a lovely womb for the rapid proliferation of multicellular life. Yet as time went on, new life and geology gradually reduced the amount of carbon in the atmosphere until an unanticipated dip, though this did recover. The vision sent the Earth into a huge extinction disaster and a glacial icehouse. The carbon sequestration mechanisms that first caused the glaciers to disappear, producing carbon. It was only temporary before becoming commonplace in the atmosphere once more. Plant life itself began to spin 350 million years ago. Emerging from a warm climate and entering early land plants started to proliferate in the depths of another ice age, which led to the fact that, eventually, these plants removed CO2 from the atmosphere and created vast marshy forests. However, much of the carbon remained trapped in the logs when they died because microbes were unable to completely decompose them. Vegetation that would ultimately be crushed into coal. This drawdown caused another glacial time at the start of the Permian that didn't finish until the same coal seams were pumped by volcanic eruptions. The environment was once again full of CO2, and as a result, the climate started warming more slowly about 200 million years ago. Less abrupt rate with fluctuations of only 1 or 2 degrees as opposed to 10 or more. This pattern persisted throughout the dinosaur era, increasing gradually with fewer departures by the time the CASC, when the planet first formed 65 million years ago, it was still much warmer than it is now, has resulted in tropical plants and animals in locations you might not anticipate. Warm house, cold house. There are areas of our globe that are genuinely here in the alien formation that will eventually be known as the Prince Creek Formation. The low twilight just about makes it through the vast canopy of ginkgo trees and pine needles, untouched by the shadows. The herbivore, like other ceratopsian species, carries a big spear while it searches through the undergrowth for a nesting location. Dinosaurs with 2 peculiar horns that resemble antlers on top, and the snow is melting, and when the northern pole tilts back towards the sun, the day gets a little longer and brighter every day. Warmth of the sun. As the long, gloomy winter days come to a close, the Alaskan springtime means dinosaurs like Pachyrhinosaurus will soon have to lay their eggs in order to accumulate sufficient heat for hatching. Yet this excited amazingly, the dinosaur is not lost or stranded in this world of darkness. However, there were others who lived here permanently, north of the Arctic Circle, just like her. The Cretaceous period had far milder winters, but the Arctic Circle is still there, and scientists, even if we don't fully understand how these herbivores managed to endure times of total darkness, we do know that they did. Both hatchling and adult bones can be found in fossiliferous locations from Alaska to, on the other hand, Siberian carnivores can be better explained by the majority of the one species of smaller polar theropod dinosaur appeared to be thriving. Alaska is home to more fossilized troons than any other place in North America. Troons were little carnivorous dinosaurs. They exist in other, lower-lying areas of the United States, indicating that this dinosaur wasn't just surviving in the frigid north, yet flourishing in a manner it was unable to elsewhere. This may be partially due to its massive eyes, which would have allowed it superior night vision, which was helpful throughout the numerous days of gloom, although there was less of a chill. The Arctic Circle saw a far warmer mean annual temperature of roughly 10 degrees C during the Cretaceous period, which was, of course, still sufficiently frigid and distant from the tropical environment most associated with dinosaurs. That neither cold-blooded reptiles like turtles nor snakes nor amphibians have been discovered yet. Instead, the environment is most accurately described as moderate, chilly, and fairly mild with the presence of a surprising. The temperate environment in what is now the tundra is not quite as odd as in the Arctic, which received just around 20. When temperatures increased during the early Eocene, around 55 million years later, millions of years ago, the temperature was gradually rising, and as it did, the tropical and subtropical rainforest changed as a result of global ecosystems adapting. Grew into a vast global rainforest that spread northward, away from the now too hot equator and into areas that were still habitable. Spanned the North Pole, growing in a warm, carbon dioxide-rich environment where ponds and rivers were home to hippo-like pardons that enjoyed corydon and labored to avoid enormous alligators that hid in the shadows. Ants, measuring 5 centimeters in length, marched through these woodlands, across land bridges that connected North America and Europe. Huge rain clouds were drained by warm summer and moderate winter temperatures, which fueled the growth of mangroves, and a subtropical rainforest along the coast made this place resemble a real heat island, having a mean temperature of between 16 and 21 degrees C at the poles. Similar to those in southern China and Zambia, although these hot springs weren't complete jungle havens, Even while the Arctic could support a wide variety of plants, the equator was almost unbearably hot. Thus, there was a migration rather than an unending expansion, averages of 40 to 50 degrees. It's crucial to keep in mind that these are maximums and not minimums. Perhaps, more crucially, maximum summer temperatures would have exceeded the already equatorial average of the horrible. The hyena, a diminutive primate resembling a taro, is among the oldest known primates. Primate whose remains provide evidence for the real extent of the Arctic's hot springs. Rainforests are found almost everywhere in Asia, Europe, and North America. Despite its small size, this primate moved swiftly over the North Pole, driven forward by a massive hyena that appeared among the fossilized remains of a vast, habitable subtropical rainforest. Record during the Paleocene-Eocene thermal maximum, approximately 552 million years ago, when the Earth was already quite warm and felt even more heat, causing the ocean's temperature to soar. The guide's resolution did discover this peculiar incident embedded in that reddish layer of dirt, and now temperatures have risen by 5 to 8 degrees over the already warm baseline, according to isotopic carbon research. A geological blink peaks and then returns to normal in roughly 200,000 years of an eye, with the cause being an extraordinarily massive carbon emission into the atmosphere over nearly 20,000 years. Radically altered the global climate, although briefly. The geological and biological conditions of our planet are always changing, and the gradual warming trend that began some 200 million years ago was about to shift as the hectic world started to absorb the extra that evolution drove additional modifications once our planet finally entered a cool house atmosphere. And one notably, the evolution of a plant that we now take for granted was a significant transition. Grass is a seemingly straightforward plant with tiny pellets embedded in its leafy blades. Contains silica that causes the teeth of those who consume them to become worn down. It can quickly regenerate from its roots. Its wind-dispersed nature allows it to recover quickly from both fires and grazing, reducing its need for animals. The earliest grasses appear in our fossil record during the Cretaceous to transport pollen, but they really started to glow in the era of mammals, considering that trampling may destroy plants and trees, but it doesn't harm grass. And during the colder months, grass took a chokehold on the biomes of the planet, spreading swiftly and starting to the earliest grasslands were open environments that altered animal life patterns, including grazing mammals in order to chew through the silica-laden leaves in broad spaces. Horses developed larger teeth. This helped herbivores struggle. They also evolved in order to hide from predators. For example, horses developed longer, stronger legs so they could run away. Others lurked in vast herds, resulting in packs of carnivores escaping their prey. In response, grasslands rewrote the rules of nature so that it is difficult to imagine a world without grass and running animals. Grass, and a colder climate in Africa, the historical homeland of our species, keep altering everything. As of now, Africa is divided into a dense rainforest that stretches away from the continent's core into huge areas of diverse biomes. The enormous savannas and grasslands that make up these jungle heartlands are surrounded by large deserts to the north. Yet although Africa has always been a warm continent, its biomes' regional identities have not always been as obvious. The habitats of today's precipitation have a major role in determining where in Africa, and today's many monsoon systems determine where. Regarding the amount of rain that would fall, historically, rainfall hasn't been that predictable. Even 30 million years ago, Africa was a patchwork quilt consisting of various habitats, including various kinds of forests, and conversely, grasslands were found in a variety of locations, each determined by the climate there. Of a continuous one, Our predecessors would have had easy access to a wide range of surroundings to take advantage of. Rather than large stretches of ecological homogeneity, this was the primate world. Egypt opus was a tiny ape that lived in trees, much like the inland forests and mangroves of what is now Egypt, but drier than the weather in the polar rainforests of eastern Africa was diverse, with various periods of short precipitation following the EO. Africa's rainfall patterns and ensuing climate have been oddly shifting, and this hasn't been due to carbon dioxide, but to modifications in other continents, particularly about 50 million years ago, when the continents of Asia and Eurasia collided. These two tectonic plates had been and ended Africa's reign. For a considerable amount of time, a massive game of rock, paper, and scissors is performed as the plates of our planet collide. Lighter continental plates prevail over thick ones, while the dense plates eventually sink beneath each other to melt and produce. At first, the Indian plate consisted of a mixture of thick oceanic crust, and when Asia and India first collided 80 million years ago, the Indian plate's light continental crust gracefully lost the match and went down. But when that border was approached by a portion of India's continental crust, the connection abruptly shifted, with each dish bearing a similarly thin crust. Challenging to break or bend, making a winner impossible to determine. Yet the shifting dynamics of Earth's mantle persisted in forcing them together, even though neither plate was dense enough to bury the other due to their equal strength. This obstinacy persists to this day, leading to the formation of a mountain range. This range, known as the Himalayas, provides evidence of the permanent separation of the two plates, battle for supremacy. But the Himalayan mountains' ascent had implications without volcanoes at all that limit the amount of carbon dioxide that is released into the atmosphere. The Himalayas remain towering, and as a result of blocking and rearranging air processes, the Asian monsoon, which now controls when and how much precipitation falls over a remarkably large area of the planet, vanished along with Africa's patchwork biomes. And over time, the continent's area where the seasonal monsoons continued to provide enough rain to sustain them was where rainforests withdrew. Grasslands grew to take advantage of the lack of trees, creating huge savannas. Our ape ancestors had to choose between following these woodlands or not. Perhaps since many of them managed to adjust to life outside of warm-house humanity, imagine a day so hot that candle wax melts in the absence of flame. Centaur. Railroad lines melted and boiled up from the asphalt. These were the signs of in 1911, there was a heat wave on North America's North Atlantic coast, bringing with it extremely high temperatures. Cities in July and persisted for 11 days, breaking records for warmth as the population suffered, with around 5,000 people spending the night on the streets. Attempting to flee structures that become furnaces without air conditioning more than all estimations are during that 11-day period, 2,000 people perished, and many of them were driven insane. Although people have already spread to every part of the globe, living in this heat is not always simple. Globe, despite what may seem, we are still not always able to handle certain temperatures. But as our climate continues to change, it's getting more and more typical. Scientists estimate that every extra summer day, over 32, 7 individuals per million pass away, while many hundreds more get sick. And in certain places, this figure might be a conservative estimate. Where it doesn't seem like 32 degrees, even though these temperatures are unexpectedly unbearably hot, especially in comparison to the days our planets endured during the heat wave, our world has now experienced a moderate and controlled icehouse temperature throughout the last 2.5 million years. The planet has experienced slight temperature variations within a significantly cooler spectrum, between 4 degree and 8 degree cooler than it is now at the lowest end of the glacial maximum periods, which were identified by the glaciers moving out of the highlands and down. These glacial stretches stretched out into the valleys and flatlands for millennia at a time. The latest of these occurred 25,000 years ago, reflected heat and light back to us, and our forebears fought through the icy wastes, and our cool climate environment has rendered humans more susceptible to heat waves. Humans have numerous adaptations that allow us to survive in an environment similar to that of the Eocene. Severe heat, even in the absence of air conditioning, all of these are beneficial, although they damage children, and among these, arguably the most basic is behavioral in the elderly and frequently in individuals taking specific medications. A fancy word for when we relocate to a spot to chill off is thermoregulation. Be as easy as locating air conditioning, shade, or a place to jump into the water to assist us in the short term and in the long run. Eventually, some people discover that they must relocate permanently from areas with intense heat. We also have a lot of physiological changes to withstand heat. Our skin has less hair and more hair sweat glands, which are dispersed throughout our body as opposed to other animals' more confined glands. Bipedalism is another example, such as in dogs that only have sweat glands in their pads rather than the rest of their body. Benefits of standing upright include reducing the amount of skin exposed to direct sunlight from above and implying that a larger portion of our bodies are exposed to side winds. Yet despite these adaptations, our bodies have physical limitations, even more so when we work out and move since our bodies generate heat. Most of the time, our internal systems are only able to withstand temperatures of about 40 degrees. When it gets really hot outside, we employ behavioral thermostat control, but research has shown that this depends on what transpires to our bodies when we are unable to identify locations that cool down. When this happens, our bodies begin to shut down. Our muscles start to cramp, particularly in our stomach and legs. We sweat palely and coolly until we run out of water, which exceeds the efficiency of our cooling system, making it more difficult for our blood to circulate when there is less water in the system. Our skin starts to redden, our heart rate increases, our blood pressure rises, and we frequently get confused and disoriented, feeling extremely lightheaded or passing out. And then we pass away, keeping in mind that the planet in several places, the Paleocene-Eocene thermal maximum averaged between 40 and 50 degrees. It makes sense that there were some locations where it would have been impossible for people to survive. Yet, as we know, the climate would change as the temperatures dropped. Impact the development of humanity one issue that people, because we are warm-blooded and unable to completely shut off our internal heating system, high temperatures. Not all of our ape ancestors suffered from the same conditions. However, certain animals like mice and lemurs can reverse their internals. This indicates that throughout the course of a day, a mouse's temperature might rise or fall. While internal body temperatures in individuals can vary from 18 to 37 degrees, we thought that hyperthermic, meaning that our body can stop heating down to just 35 degrees. Many little primates appear to be able to reduce their resting body temperature because of a structure in their bodies known as a topper, metabolic rates, relying solely on ambient heat to stay warm rather than expending energy in the process. It's a very helpful adaptation for them to find themselves in a hot house setting, but our reality was not a warm residence. Ecosystems in the cradle of humanity started to cool off forever. They grew more solitary and transparent, and our forefathers had the ability to go far farther and more effectively. This might have had an impact on the emergence of early hominins' distinctive upright bipedal stance. When walking on two legs, we move far more quickly and use less energy than when we moved quadrupedally, like our ancestors did. For instance, chimpanzees can traverse around 2.9 kilometers, but previously, being more mobile, allowed us to travel farther than the 4.5 hours that most humans can traverse. Benefit from a far wider range of environments than our quadrupedal forebears by traversing between them and making use of materials as they are found. The majority of non-human ape species live in trees. Very few have succeeded in preserving their ancestors' specializations to survive in woodland and forested habitats. A limited number of primates are found to thrive outside of tropical regions, with most residing at higher altitudes or latitudes. In ecosystems, decreased metabolic rates and torpor may be beneficial, but they're far less beneficial for humans' high metabolic rates to help them adapt to the cold enabled us to adapt to a wide range of situations and our effective bipedal. This made it easier for us to reach them. Old hominin species can be found in numerous distinct habitats. For instance, Atticus can be found in both forested areas and meadows with trees. As hominin intelligence increased and the temperature remained cold, our ancestors dispersed throughout Africa and Eurasia. Many habitats, including the China brushy lakes, the Javanese tropical grasslands and forests, and higher elevation areas in Europe where predators were less likely to prowl. Today, we live the whole world covered in snow, sand, and ice from sea level to thousands of meters above it. Our bodies were designed to be adaptable to changes in habitat, including the monsoonal rains, getting ready for us to adjust to a wide range of ecosystems when the climate got awesome. And after we learned to walk on 2 feet, a lot of additional behavioral adaptations in humans became easier because our hands were free to hold tools and we could carry tools with our kids. Grew more adept at foraging, which in turn supplied food to sustain larger, decreasing temperatures and diverging environments. This appears to have steered monkey evolution away from small brains in this way, from large-headed, widely dispersed primates to heat-resistant monkeys confined to trees. Being that humans are now, we ought to be appreciative of our internal temperature. As long as we continue to hold on to it, and it's evident that the altering environment had an impact on our development, although it's still unclear exactly why it was cooler than in the Eocene. Why did the Earth freeze? Approximately 56 million years ago, our forebears would have possessed perhaps an old hyena perched on its preferred tree, looking out into the distance, and marveled at the bloom, which covered the river in a thick layer of green. These plants, which were composed of millions of tiny mosquito ferns, were so widespread that their remains can be found filling up Arctic Ocean sediment cores today, as well as at brief periods in the early EO. These aquatic ferns must have covered nearly the entire scene because they were so prevalent. Even more peculiarly, this plant, known as Aola, is found throughout the Arctic Ocean. The Arctic Ocean was lush, warm and fresh, and only suitable for growth in freshwater. Carbon is the cause of all water. Today's atmosphere has significantly less carbon dioxide. Instead, the carbon on our planet is stored elsewhere. In fact, a variety of materials can be used to store carbon swamps full of logs that are kept from decaying. During the Carboniferous coral reefs, and stored a large amount of it in colony structures is retained by rocks, particularly those found in the Himalayas, where carbon can mix with the rock. By a process called weathering, and this silt loaded with carbon eventually finds resting places in rivers. This indicates that there is more exposed rock in our waters, particularly if that rock is more carbon may be stored in areas rich in silica, and the Himalayas have revealed an extraordinary. Over the past 50 million years, a significant alleviation of rock has caused our atmospheric carbon to sink into the set off the shore. Of India, it's also done so close to the equator, causing weathering and precipitation that otherwise may not have occurred. Although the majority of geologists believe that the mountains would have originated closer to the poles, the Himalayas most likely received assistance from other carbon storage sources, so they did not alter our atmosphere entirely. Systems which comprise oceanic water, We witness a number of odd alterations in our oceanic habits during the Eocene, one of which is the shift in the Arctic from a salty ocean to a freshwater environment. A lake devoid of salt indicates that the Arctic Ocean was probably closed off, and even though it is now isolated, the Arctic Ocean still moves around the Earth, passing through areas like the Bering Strait. However, at the height of the EOS, between Alaska and Russia and the Greenland Sea between Greenland and Norway, the majority of these spaces were absent from the scene. Instead, they were stiffer and higher. Ocean floors, which might have contributed to sealing off the Arctic and fostering the growth of freshwater algae, cutting off the Arctic Ocean completely alters the water in other places, not only creating an odd freshwater environment. Additionally, the Arctic supplies some of the world's coldest water, so it has a significant impact on function in ocean circulation. Warm equatorial waters rise while cold Arctic waterfalls. Run-rise generates currents that maintain stable ocean temperatures and guarantee the survival of the lowest ocean waters. Moreover, extremely cold waters dissolve more gases, accumulating enormous amounts of CO2 in hot waters at ocean depths without Arctic Ocean influx. The planet's oceans warmed more uniformly and held less gas, which contributed to the elevated CO2 levels observed in the EOS picture. Although this mechanism is self-regulating, the land that encircled the Arctic could only be so tall, and with increased precipitation and meltwater in the Arctic and certain tectonic shifts as well, until the Arctic Ocean finally overtook its banks, causing the bathtub ring of rocks to disintegrate and flow into the seas and straits. We witness it playing a bigger part in controlling CO2 and temperature nowadays. Storage. And because of this small, but we can roughly pinpoint when this occurred. Arctic sand is dominated by fern Aeola, an abundant mosquito. Cores between 49 and 48.3 million years ago, when it abruptly vanishes, the Arctic Ocean's salt content will return, and the world's climate will shift to what it is today. Nevertheless, there are still more mysteries surrounding this fern, which may have more to do with the present carbon catastrophe than we think. Acknowledge that although all plants absorb CO2, some do so more than others, and Aeola is a rapacious breather. In fact, some scientists estimate that the amount in the Arctic alone, between 50 to 470 parts per million of carbon dioxide, may have been eliminated by Aeola. For comparison, during the current rainy season, there are roughly 418 pieces per millions of tons of carbon dioxide are stored in the atmosphere overall, thanks to this amazing carbon storage. This is the reason some scientists are considering Aeola farming as a way to reduce our existing carbon footprint issue. And yet, it appears that the Arctic AA's time frame does not exactly correspond with our planetary shift. Therefore, it's unclear if AA's contribution to the decrease in CO2 was in the real, significant, or just unrealized potential. So in the end, assessing the components that contribute to historical climatic shifts can be challenging for businesses. The hothouse maximum may have been created in part by volcanic activity, but subsequent eruptions could actually contribute to both the creation of acid rain and the cooling of our planet. Dioxide can offset some of the CO2's heating components in our atmosphere. Thus, taking a broad look at climate shows how flexible our world can be and serves as a reminder. The ephemeral nature of life is underscored by the fluctuations in worldwide temperatures. The world becomes a brand new, singular version, with enormous polar extremes melting and reforming rainforests spread around the world and becoming into the desert ecosystem, with flora and FAA regulating the atmosphere above the oceans nearby and the tectonic tremors beneath. A shift in any one place can result in numerous species will vanish from one environment while others will replace them and flourish in the other one. Planet, of which we are a part, and without the Earth's transition from a hot, You've been witnessing the entire history, from house to cool house to ice house. Without you, our narrative would not have ever started. Thank you for watching. Do not forget to like, subscribe, and comment to let us know what you think. We will meet again